We're going to take a look at a problem right off of the review sheet. It says Gary Sledmore went to Lakewood Forest Preserve to go sledding over winter break. The 25-kilogram boy grabs his snow tube and gets a running start at the top of the hill, which means we're going to have some kinetic at the top. At the bottom of the 10-meter high hill, Gary is traveling at 20 meters per second, so we're given the velocity at the bottom. How fast was Gary Sledmore's running start? The first thing I'm going to do is I'm going to draw a picture and label the velocities and the heights that I have. So I've got Gary Sledmore in place. I labeled the hill as being 10 meters high. I've got a velocity at the bottom of 20 meters per second. Now it's important to note you're going from a high position to a ground position. We're looking at energy at the top turning into energy at the bottom, and this is conservation of energy. So I'm going to label out both potential and kinetic at the various locations. At the top of the hill, we're just going to label out what total energy would be. It would be potential and kinetic. In this case, we know that there is some velocity at the top, and we're trying to figure out what that is. And then at the bottom, there's potential and kinetic. And right off the bat, we know there's no height, so we know that potential is going to go away because there's no h, but we'll take care of that in a minute. So we're going to set up a conservation of energy equation. So as you take a look, we've got conservation of energy. You got PE at A plus KE at A equals potential energy at B plus kinetic energy at B. We know these things are going to be equal. And now that we have that set up, and that's how I start every one of my problems, now I'm actually going to put in the equations for potential energy and the equation for kinetic energy. So now I've got my equations in place, and one thing I want to point out, even though the problem tells us that the mass of the boy is 25 kilograms, we've hopefully learned at this point that if there's a mass in every one of these equations on either side of the equal sign, we can actually cancel out mass. Secondly, if you look on the right side of the equation, the height at the bottom of the hill is 0, so this equation right here goes to 0. We're left with the GH on the left plus the 1/2 V squared on the left equals the 1/2 V squared on the right. The V squared on the right is the 20 at the bottom of the hill that we're given. The H on the left is going to be the 10, which is the height at the beginning of the problem, and we're going to be looking for that velocity up at the top. So I'm going to plug some numbers in place and then do some algebra. So I've plugged in my numbers. I'm remembering that I'm solving for the velocity on the top of the hill, which is on the left side of the equation. So at this point I'm going to put numbers into my calculator. Now the value over here on the right in my calculator ends up being 200. And because the two values on the left side are added, I'm going to have to subtract out the 9.8 times 10 from the 200 on the other side. So in order to do that, I'm going to be left with 1/2 V squared equals 102. Now I need to take that 102 and I need to multiply by 2 to get rid of the 1/2. And then to get rid of the square, I'm going to take the square root of that value. So I end up getting a velocity of a running start of 14.28 meters per second. Now, for those that understand what that looks like, in miles per hour, that's approximately 31.9 miles per hour. So that's absolutely ridiculous, but that's the fun of the problem in Gary Skidmore. Now, the idea, though, is using conservation of energy, you can solve for velocities at the top of the hill, at the bottom of the hill, in the middle of the hill, on a second hill. Typically, you're going to be given all the heights, or you'll be given enough of the velocities that one thing is remaining that you can solve for.